Welcome back. This is part 2 of the workshop, How to Teach Science and Engineering. This workshop is made for science and engineering teachers, lecturers, TAs, assistant professors, etc. Even high school teachers. Okay, in the last lesson you learned about honestly finding out the truth and telling the truth as much as you know, not to copy blindly from the books. Okay? So, did you find anything wrong with the part 1 of my presentation? Should have gone over it again, questioned everything. That's another thing I taught you. You must verify. Do not believe anyone 100%. Verify. Okay? For example, I talked about the shape of the earth. Okay? And I showed it to you through calculation that earth is very close to a sphere, not exactly a sphere. It is called oblate spheroid. But I did not mention that name. You should have caught it. Oblate spheroid, that means almost like a spheroid, sphere. Oblate means slightly flattish here and there, okay? Because this part actually bulges out because of the centrifugal force, which is a little bit too complicated to understand. But I'm just saying that you should have checked it and mentioned this name, oblate spheroid, if you are teaching young students. It's not exactly a sphere, but very close to a sphere. Definitely not flat, that much flat like this. Okay? All right. There are many other things you should have probably caught, but that's okay. That's okay. Let's go on to, you learned about Newton's first law of motion from scratch with imagination. And that's what the students have to learn. They have to stretch their imagination. How do you start teaching Newton's laws of motion? We're going to learn Newton's laws of motion. First law is this, second. No. Start from the idea. Sometimes that's what you have to do. Okay? Make them think like they can be as great as Newton. Let them think. Let them imagine. Interact with them. It's not possible in every lecture. I understand that. But as much as possible, especially the first few lectures, so that they start liking you, start liking your teaching, enjoy coming to your class. Their mind opens up. Okay? It's very important in teaching. Otherwise, science can get very boring for most of the students. I'm telling you, because the results show 80% of the students don't understand it. They are scared of physics, which is the fundamental of science. Okay? All right, good. They can memorize, pass, and grade, and get 85%. That's the pass marks in West Bengal. How come we are not producing hundreds of J.C. Boses, Meghnad Sahas? We have to admit that we are doing something wrong. Let's correct it. We are teachers. We are creating future. We have a huge responsibility for the future of India on us. Okay, entire world, the future generation is much more important than our generation, to be honest. Okay, explain the concepts, give them some samples, show them some experiments, make them understand, and then encourage them to solve some more problems. Okay, we are going to go over Newton's second law of motion. Okay, yesterday you learned about how to teach the first law of motion. You know these laws, but I'm just telling you how to explain it to young students. Okay, talking about the inventors and all of that brings some interest. Oh, really? Oh, okay. Newton came up with many more things than just these laws. Yeah, he has worked on light, on heat, and sound, mathematics. One of the founders of modern calculus. The other person was Leibniz. Okay, He was from Germany, Newton was from England. Okay, so talk about a little bit more than what's written in the book. They can read. They'll read anyway and memorize just to get some kind of grades. Have they understood? Can they apply it? Can they solve some realistic problem? Are they fit to join industry? That's what you have to see. That's going to be real progress. Okay. Part 2. Newton's laws of motion. We will continue with Newton's laws of motion. First law, you saw that body at rest stays at rest until and unless some force, external force is applied. Body in motion continues to move at a constant speed in a straight line until and unless some external force is applied. Then it changes, okay? Good. You can ask them questions like, okay, you are standing on the floor. And then you start to move. Where did that external force come from? According to Newton's laws of motion, you need an external force. Where did that come from? Ask them. Okay, very important. Let them think some other time, when they are in the evening, they are sitting alone. Let them think, really, how do I move? Is Newton wrong? If Newton is right, and this law is right, where is that external force coming from? Good. Now that we know that force causes change in motion of a body, okay, sometimes there's equal and opposite force, etc. We'll talk about it later. We don't need to confuse them with too many things at a time. Okay, changes motion of a body. Scientists are not happy with just this kind of qualitative description. Qualitative means, okay, you apply a force, it starts to move or changes the motion. Qualitative, there's no number involved. The quantity is not involved. They like to know quantitative relationship between the force and the motion, for example. How much force should I apply to get this kind of motion? If something has this kind of motion, how much force is being applied? That kind of, how much? That's the question. That makes it quantitative. Quantity, need number, unit, size, okay? How much force changes the velocity by how much? That's what we'll do now. Okay, suppose I have a body, I apply a force, and it's got some velocity. It starts moving in that direction. If I apply the force in this direction, velocity. Suppose it was stationary, it starts moving in that direction. That's what it is. And the body has a mass m, okay? Now, think about it. It starts to speed up from 0. It goes slightly faster, then faster, because I'm applying a force, right? This daily experience we have. Velocity keeps increasing. That means it has an acceleration. Rate of change of velocity is acceleration. So if I apply a larger force, what happens? The rate of change of velocity would be higher. Look, a constant velocity does not need a force. Okay, that's first law. So when you get a constant velocity, that will maintain that. We are talking about quantity of force, rate of change of velocity. That's the acceleration. Okay. So if I apply a larger force, the rate of change of velocity, that is acceleration, would be higher, right? Okay. So can we guess that the force is proportional to the rate of change of velocity? If this is higher, acceleration is higher. That's logical. Okay. That, the first assumption we can say is, if this doubles, that doubles. We can verify later whether it's really linearly proportional or not through experiments, but let's assume it's the first assumption that the force is proportional to the rate of velocity. Now there's one more thing. Can we say that to accelerate a larger mass, you need larger force. If I take something very small, very light, very little mass. By the way, do not say mass. It's mass, both in British and American English. It's mass, okay? You can check the dictionary. Mass, a small mass, okay? And if I apply a force, it accelerates. If the body was much larger, very heavy or larger mass, to accelerate by the same amount, I need larger force. You have to think about it. You push a little bicycle, it accelerates. To push a car, to bring it to the same speed, to cause the same acceleration, you need much larger force. You need to push very hard. Okay? So let them think about these things. Yes, that's making sense. So it depends on mass too. And thus, the force may be proportional to the mass too. Okay? Larger mass, you need larger force. So these two put together, Newton started thinking that what is it that actually relates to the force? Acceleration, mass, both. So he thought every body, material body, has something called momentum. He combined velocity and mass together by multiplying them. It depends on mass and velocity. He defined this property called momentum of a body. It's conceptually difficult. It's not that easy. Students just don't get it just by reading definition. Okay? You have to explain in various ways. Newton thought about this and came up with an idea that there could be something like momentum, just like force, but force we feel, so we understand right away. Right? Even before, many scientists knew about force. Average people know about force without reading physics. But he had to define something artificial called momentum, something that depends on mass and velocity both. Okay? Small mass, small velocity has very little momentum. Small mass, high velocity has higher momentum. Large mass, same velocity, has larger momentum. Large mass with very high speed has even higher momentum. Okay, so that concept has to sink in. Of a body, which is mass times the velocity, mv. So if that's a body, I'm drawing a simple thing. It could be round, it could be any shape. It should have a mass, m. If it's got a velocity v, it's got a property called momentum. It's kind of like inertia. If it's got large mass and velocity, it wants to keep moving the same way. It doesn't like change. It's like inertia. Momentum, okay? Mass times velocity. Good. Give pause so that they think about it. Ask some questions. Let them ask you questions. So what is this momentum? Can you explain in a different way? Give some other example. Okay? Come up with your example. First, it should be clear in your mind. Then you come up with the example, understand it fully. Then you think how to explain to somebody who's hearing about it the first time. It's not easy. Newton took years to come up with this concept. You cannot just explain it to you in 2 minutes. And they are not Newton, okay? You have to understand that. They're very young kids. Okay, when we apply a force, it's the momentum that changes. That's what he thought. Newton thought. And Newton thought that the force is proportional to the rate of change of momentum. Rate of change of momentum means, rate means not by price, with time. With time, how things motion has something to do with position and time. So how with time it changes. Per second, how much the momentum changes. Okay, the force is related to that. What is momentum? Mass times velocity. Rate of change of momentum, how fast that mass times velocity is changing. That rate is related to the force. It will take a long time to sink in. Such a simple concept for us, but actually it's very difficult. Not very intuitive. Momentum, what is momentum? Okay, so let's say somehow you explain that. Then you say force is proportional to the rate of change of momentum, mass times velocity. I'm writing this x as times. Do not call it into. Into is wrong English. It's got a different meaning. Say mass times velocity, or mass multiplied by velocity, okay? That is the change of momentum mv. Change of momentum per second is the rate of change of momentum. So force is proportional to this. What does proportional mean? Proportional means if I draw this quantity, F, on one side, plot, and other side, the other quantity, the rate of change of mv, momentum, there is a linear relationship. If this doubles, that doubles. If that triples, that triples. Linear, okay? If this yeah, well, that's not always true. The slope could be different too. So find some other explanation. Let's say if this increases, that also increases. That increases too. Okay? So it's linear. It's linear. Okay? So Newton's second law of motion, he just summarized that way, that the force acting on a body is proportional to its rate of change of momentum. That means if I take a body, apply a force, it will have some kind of acceleration, but I have to calculate the rate of change of momentum, mass times velocity. How much was it here? After 1 second, how much is the mass times velocity? The difference of that will tell me in 1 second change that much. That will be equal to force. Slow down, slow down. These are very, very difficult concepts, but these are the fundamental of physics. If you do not clarify these things now, the difficult concepts, they'll never get it. They'll memorize and they'll make mistakes, okay? All right. So let me write down that Newton's second law of motion one more time. The force acting on a body is proportional to its rate of change of momentum. How much is the momentum changing per second? That will be equal to the force. Okay. Suppose for a body, the mass does not change. We'll assume most of the bodies that we see, mass does not change. Mass remains the same. So 1 kilogram stays as 1 kilogram unless you divide into two bodies, okay? Or cut out a part and throw out and say, this is my body now. Generally, for a body, the mass remains the same. Mass remains the same, okay? The mass does not change. So F equals rate of change of mv. M does not change. We can take that outside. Okay. In mathematics, it can be shown that if I'm talking about two quantities, one does not change and they're multiplied, I'm taking the rate of change. The constant part can be taken out. Explain it with some simple example, maybe. Just fix it at 2 kilograms. Okay. You can show that rate of change of 2v is the same thing as 2 times the rate of change of v. Okay, put some number for v. Okay, we can define, or F equals, what is rate of change of velocity? That you must have learned the first earlier lessons in physics, in kinematics. Rate of change of velocity is called acceleration. Force becomes proportional to mass times acceleration. Force is proportional to mass times acceleration of a body. Okay? If it is proportional, like the line you saw earlier, the straight line, we can say the slope of that line, or proportionality constant, times mass times A. This proportional, we can remove that and make it equal to constant, proportionality constant, okay? And this is how proportionality can be converted into equality, okay? Some kind of constant, the slope of that line that you saw, multiplied by mass times acceleration. So A is the acceleration there. Now we can define the unit of the force. See, force, we have only talked about force, that force is a cause of motion. but we have not assigned any unit to it. We can choose our unit. Okay, we can call it something, some number, unit force or something. So we can define it in such a way that this proportionality constant becomes 1. Then we'll get a simpler formula, F equals ma, but we have to be careful about the unit of A now. So this is the famous formula of Newton's second law of motion. F equals mass times acceleration of a body. That's the mathematical form of Newton's second law of motion. Very important formula. Very important formula. Okay? One of the most important formulas that you'll come across in fundamentals of physics. We'll talk about where these formulas can be applied later. Okay, so if I have a body, if I apply a force, it's got a mass m, and the velocity keeps changing. If I apply the force that way, which way will the velocity increase? That way, same direction. Okay, so that's an acceleration, rate of change of velocity is acceleration. Newton's second law of motion says this force will be equal to mass of the body times the acceleration, which is rate of change of this velocity. Okay, good. For example, if I have 1 kilogram mass, suppose this, how much is 1 kilogram? It's a defined, predefined unit of mass. Roughly, let's say about that much of iron would be 1 kilogram. Many students don't know how much a kilogram is. Show something like that much of wood. Bring a weight, for weighing 1 kilogram. So that's 1 kilogram. Okay, they should get these ideas. It's very important to get realistic feeling for things, not only equations. F equals ma. Let us say it's 5,000 kilograms. How much is 5,000 kilograms? Do you know? Can you imagine? What's the weight of a truck? What's the weight of a car? What's your weight? I'm saying weight, but I mean mass. Okay, all right. Realistic feeling is very important. And a feel for the numbers and units and size, all these things are very important. If I apply a force that causes 1 meter per second square acceleration, I hope they understand this acceleration, the rate of change of velocity. If the velocity was 0, it becomes, after 1 second, it becomes 1 meter per second velocity. That acceleration would be 1 meter per second squared. Okay, then that's, if I apply a force on 1 kilogram mass and it causes 1 meter per second square acceleration, that force we'll call as 1 Newton. That's what it's called. It's also written with shortcut N, Newton, to honor this great physicist. In his name, which was Newton, that's now almost worldwide accepted standard unit of force, Newton, 1 Newton. So how much is 1 Newton? If I take 1 kilogram mass and apply a force and measure the acceleration, and if it turns out to be 1 meter per second squared, that force is 1 Newton. Okay, so 1 Newton equals mass 1 kilograms times 1 meter per second squared, using this formula, F equals ma, and that gives me 1 on both sides. 1 Newton equals 1 kilogram meter per second squared. Kilogram comes from here, acceleration gives this. We can also write the unit as kilogram meter. The second squared becomes -2 when I move it on top. The power, raised to the power, -2. So you have to know how much 1 Newton is. It's a force that's equal to the same thing as 1 kilogram meter second to the power -2 per kilogram meter per second squared. But physically, how much is a force? We'll talk about it. How much is 1 Newton force? If I apply a 2 Newton force on a 2 kilogram body, how much acceleration will it have? You do it, you ask your students to find that too. Plug in back in the same formula. Force equals ma. 2 cancels, a is definitely 1, right? The same thing. 3 Newton on 3 kilograms will cause 1 meter per second squared acceleration. Change these numbers a little bit, ask them to solve 1 or 2 more problems till it sinks in. They would make mistakes because they have to flip this formula to find acceleration. They have to divide force by m, mass. You could change just a couple of examples, these numbers. All right. 1 Newton is not a very large force. If you press something with finger, that's about 50 Newton, an average person. Okay? 50 Newton. I just did the experiment. I took the bathroom scale, pressed it with one finger. It showed about 5 kilograms. 5 kilograms multiplied by G, which you know is approximately 50 Newton. It's not a big force, 1 Newton, very small force compared to the force we can exert. Okay? 1 Newton is not a very large force. You may be able to apply 50 Newton force with your finger. Okay? And 500 Newton force when you're lifting heavy weight, like 50 kilos, you can lift. I can lift 75 kilograms, okay? 500 Newton force multiplied by 9.8, approximately 10, okay, all right. While pushing a car, we can put a lot of force. I have not measured it, but I'm guessing maybe 500 Newton, even more. It's only 50 kilograms. We can do much more while pushing a car, okay, or pumping iron. Okay, that means exercising. Suppose a 1,000-kilogram car is stationary. Relate all these things immediately to something realistic so that the idea and the numbers sink in, the size in the mind. It gets almost hardwired. Okay. Suppose a 1,000-kilogram car, do not say 10-kilogram car or 50,000-kilogram car. Be realistic. 1,000 kilogram is a slightly heavy car, mid-sized car. Okay. There are SUVs that are over 2 tons, 2,000 kilograms. So this is realistic number. Always take realistic number. Okay. 1,000-kilogram car, stationary, and 4 people push it. For some reason, they have to push it. It's broke down. The car is not working. They have to push it. 4 people push it, and each with a force of 500 Newton. Each is important. Sometimes students forget to read English very carefully, and they make a mistake. Each 500 Newton. We saw that 500 Newton force is not too big. You can apply it if you really push hard. How much is the acceleration? What will be its velocity in 1 second? You can even say, how far will it go? Okay. So, how are you going to solve it? We know Newton's second law of motion relates force to motion. That we need to use Newton's second law of motion. F equals ma. How much is the force? 4 people, each pushing at 500 Newton. With 500 Newton, 4 times 500 Newton, 2,000 Newton, okay? Or 2 kilonewton, small k, large n. Newton is always written with large n, okay? All right, how much is the acceleration? We know force, we know the mass. Acceleration, we just reverse this formula, divide both sides by m, F over m, mm cancels, equals A equals F over m, force divided by mass, equals 2,000 Newton divided by 1,000 kilogram. Make sure they are using Newton and kilogram. It's very important. You cannot mess up. Instead of kilogram, you cannot put milligram or gram. It will give completely wrong unit. They will be confused. Units are very important, probably as important as the formula or the number, okay? Unit. So I get 2 meters per second squared. Acceleration. I chose easy numbers. Give easy numbers so that they can, by hand, they can calculate. It's not test of mathematics or mental calculation. Physics is not nonsense, okay? Understand the concept, that's more important than use the calculator. I don't know why people say, oh, you cannot use calculator. Why? Which century are we living in? Okay, give it to them. Teach them how to use a calculator. Give it to them. Verify. Do it twice. Do it differently. It will be better than making a mistake in the mind. Are we teaching physics or how fast they can calculate in their mind? Probably genius could do 5,024 multiplied by something. Oh, what's the use? That was 100 years ago. That was the biggest talent. Okay? All right, good. Let me not digress. I can talk about a lot of other things that we do wrong. We are not keeping up. We are not keeping up with the modern science and progress in technology. Okay, A equals that much, so acceleration is 2 meters per second squared. In kinematics, you must have taught velocity is u plus initial velocity times acceleration times time. Okay, this times time. English can be confusing, but that's how it is. Sorry. You lose the war, you have to learn the language. That's how it is. U equals A times time. Initial velocity was 0. Stationary, 0 velocity. Okay. Plus acceleration we just calculated 2 times 1, 2 meters per second. 2 meters per second. After 1 second, its velocity is going to be 2 meters per second. Okay, if 4 people are continue to push. Okay, how much distance would it have traveled in 1 second? It was 0. Use this formula, ut plus half a times squared. Okay, so initial velocity was 0 times 1 second plus 1/2 times acceleration is 2 times squared. So half and this 2 cancels out. This is 0, 1 meter. It will travel. In 1 second, it will travel 1 meter. They'll be so happy that they could understand, oh, 4 people will push with that much. A car, in 1 second, it will travel 1 meter. We are ignoring the friction because we have not taught them about friction. Tell them that, road tries to slow down the motion. Okay, so you'll probably not reach 1 meter, maybe slightly small, but rough calculation, this is good enough. Based on Newton's laws of motion, now they know how from force they can calculate acceleration, from acceleration how they can calculate velocity at some time. Independent variable here was time. One could reverse the question. So if the same acceleration, the same push, the same force continued, in how many seconds it would go 5 meters or something, okay? Make them understand through these realistic questions. Then you tell them something else, okay? How about your bicycle? They're not a car. They'll be surprised. Wow, acceleration is so high. If enough one person pushes, the mass is small. Good. Oops. Now it comes to the picture. I should have shown the picture earlier. Okay, but you guys are all grown up, so you know what it means. So now I'll give a question. If a car, let's say a small sports car, 1,000-kilogram car accelerates from 0 to 100 kilometers in kilometers per hour. Now here you tell them it's not meter per second. They have to convert kilometers per hour to meters per second to be consistent with units. Units are very important. In 5 seconds, pretty fast car, 5 seconds, 0 to 100 kilometers per hour. How much force is needed? Where is the force coming from? I'm not pushing it. You could take a break and explain how the cars move. Do you know how the cars move? The engine tries to rotate the tire, the wheel, through some mechanism. Engine tries to spin the wheel. Now, because of the friction between the road and the tire, it does not allow this car wheel to spin on the road, okay? It resists, that's friction. That frictional force is stopping this wheel from rotating. So there's a frictional force acting on the tire in the forward direction. Very difficult. It's not that easy to explain. But if somebody is very smart, you should take the time to explain. Somebody has interest. Okay? So this one doesn't spin. The wheel is rotating. It can be shown that this wheel will put a force on this axle with the links, okay, with the suspension. The whole car starts moving, pushes the car, all caused by this frictional force at the bottom of the wheel. Okay, so the force on the car is acting forward. That frictional force, the front wheels, suppose this front wheel drive, sure, it pushes forward too. Okay, all right, good, but let them understand how to use this formula, what all they can do. Okay, you solve that problem too. Okay, did not say this is simple, this piece of cake. I'll give you a problem you will not be able to solve. Let me tell you that. Okay, based on Newton's laws of motion. So please, all of us should be humble. Let's think about momentum. Momentum is a very difficult concept. Let's think about momentum. The more the mass, the higher the velocity, the higher is the momentum, even if one of them increases mass or velocity. So give them examples like small thing traveling at small velocity, small momentum. If it's just stationary, it's got zero momentum. It's got mass, but zero momentum. You can think of it like this. A bicycle traveling slowly is easy to stop. Small force can stop it. Okay. Bicycle traveling fast, you get a lot of force to stop it. A truck moving at a slow speed, let's say our bicycle speed, it's got a lot of momentum, much more than the bicycle. It takes a lot of force to stop a truck because it's got a lot of mass, because of the mass. Velocity is the same for both bicycle and truck, let's say, slow-moving truck. But still, it takes a lot of force. So momentum is something very important. Mass times velocity is important. Both are important, mass and velocity. Okay. If a truck is moving at a very high speed, it's got a lot of momentum. It will take a lot of force to stop the car. Where do you get the force? Yeah, you apply the brakes, but then finally, external force, friction. This time, the friction acts the opposite direction, the road friction. Think about it. Okay, good. Momentum, one should think about. How did Newton come up with this concept? Mass times velocity is an important thing. It's called momentum. I'm not sure if somebody else used that term momentum before him or came up with this concept or not. I'm not sure. But Newton definitely wrote it down in his book, Principia. Momentum, mass times velocity. But remember, force is not momentum. Many people get confused at that age. Force is the rate of change of momentum. Momentum stays constant if we don't apply a force. If a body is moving at constant speed, it stays at constant speed. That's the first law. So mass times velocity is constant. If you want to change that, you have to apply a force. And rate of change of momentum is equal to the force, because we chose a special unit. Okay, rate of change with time per second, how much? Okay, these things are not easy. Rate of change, what? Rate of eggs, probably they know. Rate of vegetables, rice. Rate of change of momentum with respect to time per second, how much is changing. Some students are bright. They'll know as much as you do, even faster, just by reading book. Focus on the average students, which forms probably about 70–80%. Okay, if somebody is really weak, spend some extra time. But you cannot slow down the entire class because of a few students. Cannot speed up because of a few bright students. Okay, average. Focus on the average. Newton's second law of motion is very useful, and it is applied. I made some grammatical mistake here. It's very useful and is applied to solve thousands of problems. That's true. Anything that moves, if you want to analyze that, how much force is needed? Or it's so much force, how fast it's going to accelerate. Anything that moves, you need Newton's laws of motion. Okay, it's used in design of cars. If you want a car to go at a particular speed, there will be some forces involved you need to calculate using Newton's laws of motion. Robots, if a robot arm has to move this to there very quickly, how quickly do you want to move? Well, you need so much of force. What's the mass of that body? Yes, that's the force you need. Then you design the robot arm. Otherwise, the robot arm may be too heavy, too strong for a small thing. You're wasting a lot of money making too strong arm. Or too weak, it may not be able to do that. You'll pick up wrong motor for the robot. Okay, so you need Newton's laws of motion. Train, yes, it moves hundreds of places in design a train. You need Newton's laws of motion. Each part that moves, you need to apply Newton's laws of motion to find out how much force is going through it. If it's too much force, you got to design it properly or it's going to break. Rockets, yes. I'm a rocket scientist. Yes. Rockets, we use Newton's laws of motion that he found a long time ago. About 300 years ago. Anything that has motion, you apply it. It tells us the relation between force and acceleration. Of course, mass is involved in the formula. They should understand this. Now, can you think of a situation where the mass of a body is changing with time? We have used in the formula, we took out mass from the momentum, and left it to the acceleration, rate of change of velocity. Actually, the loss is regional one. The concept was rate of change of momentum. Right? From there, we derived F equals ma, which normally we use. But what if the mass is changing? Normally, if you take a body, its mass is not changing, it's constant. Okay, shape can change or whatever, unless you pull it out and break it into two parts or throw something into it, the mass remains constant. But there are situations where mass is not constant. Okay? For example, a plane, airplane, a rocket, airplane is loaded with fuel. Say fuel, not fuel, fuel. Loaded with fuel before it starts. Let's say a passenger plane may have several thousand kilograms, maybe 100,000 kilograms, 200,000 kilograms of fuel. And that burns through the engine and goes away, right? Forms, takes oxygen from the air, burns, becomes carbon dioxide and water, and goes away. So mass is reducing because fuel is being depleted. Fuel is reducing, so mass of the airplane is reducing. So I cannot take the mass out of that equation. Okay, I have to leave it with the velocity. Mass times velocity, that's the momentum. Then calculate how the rate of change of momentum relates to force acting on it. Okay, the same thing with rockets. Rockets, 99%, no, let's say about 90%. Yeah, about 90%. It's just fuel. It just burns off. When it takes off, it's a heavy, maybe something like 1,000 ton. Okay? Heavy rockets. And it's going up and up. Most of the fuel is burnt and gets ejected. So actual rocket's mass reduces a lot. Force is about the same. In the beginning, the rocket takes out, fuel is getting burned, but the force remains almost constant. Let's say, almost constant. Force is constant. Mass is reducing. What will happen to the acceleration? Accelerates even faster and faster. It takes off, slow acceleration. Mass reduces, accelerates more. Acceleration changes. Okay? Good. Good to know. Come up with many ideas, not only my ideas. I'm just giving you some idea how to teach so that students spend a lot of time thinking about that. Even if you create 10 top scientists from your class in 30 years of teaching, you know how proud you will be. I have taught this person. That person will say, yes, this teacher was very good. You'll do a great service to the entire humanity. All right, good. Can you come up with an experiment that can be done in the class to show that F equals ma is true? Today, I did not really do any experiment. I just talked about things, some ideas, and this is linearly proportional, etc. Look up the internet. There are some simple, tiny little table with a force applied through a thread and a weight, different weights you can put, different forces you can apply. Weight meaning mass, I'm talking about mass. Sometimes I misspeak. Mass, and measure the acceleration. It's difficult. Forget about stopwatch. Now you can take video with your cell phone and then say so many seconds, okay? Do that kind of experiment in the class. Make the students design it. Create that just on a table. Very simple thing, okay? All right, show it to them. There's nothing better than seeing things move and work, okay? Do that. Thank you very much. In the next lesson, I'll talk about Newton's third law of motion. I'll give you a hint right away. If you push on a book or a table, do you feel anything on your hand? You feel that there's a force in your finger. Where's that force coming from? You are pushing the table with your finger. Table is actually applying a force on you too. Okay? Good. I'll talk to you. I'll see you all in the next class.